like they've changed the way the recorder is working. Okay, so I am recording, and first I'm going to share my desktop with you so you can see what I have open here. Again, I just want to show you, here's our course. We're currently in week 4. And again, I have not set up any new material for this week. Okay, so what that means is we'll get through as much of the review as is reasonable today. Okay, I usually try, I know sometimes I run to an hour and a half, and I think that's too long. Okay, I'd like to keep the sessions to about an hour because I know it's harder to pay attention in this environment than it is in a person-to-person class. So let's see how far we get. But I'd also like to encourage you to bring questions to these sessions. So we'll have a session today and one on Wednesday. Bring your questions, the things that you're struggling with, okay? From reviewing the grades that I'm seeing, some of you are doing spectacularly well, no questions. Others of you, you're struggling. So I would say go through the homework and bring those questions with you. Okay, if you don't have them today, bring them on Wednesday. Okay. Also, I'd like to encourage you to be a little bit more flexible. It's kind of hard to type in the chat all the time. So don't hesitate, to unmute yourself to ask a question. It's not likely I'll have 20 people talking at once. And if we do, we'll deal with it. Okay. So I would like to make the class a little bit more interactive. So you feel like, you're participating and you're actually part of a learning community, which is really what we are here. Okay. So that said, here is the practice for exam 1. See this PDF file right here? So if you haven't already looked at it, you might want to look at it as we're, going through it today, right? So what I'm going to do is ask, first of all, anybody questions about what we're doing here? We're reviewing for an exam, and I'm taking questions from Unit 1 and the first half of Unit 2. Okay, so if nobody has questions, okay, I'm going to bring up the review in format so I can write on it, and I will share that with you. Okay, so let me share my tablet with you. All right, so hopefully everybody can now see practice test 1. All right, so again, what I'd like to do, if it's all right with you, is go through this, but ask you the questions. And again, I would encourage you, rather than type in the chat, even though I'll keep the chat open, okay, is just answer the questions like you would in a regular classroom, okay? There is the ability, if you want, okay, to raise your hand, okay? The way you do that is you essentially hover over your name in the participants list, okay, and then you click on hand raise. To be honest, I think that's kind of clunky, all right? And basically, what I'd like to just see is just shout out the answer, okay? So we have a graph over here, okay? Anybody know what type of function we've graphed here? Okay, take a look at the graph. What kind of function is that? Anybody have any ideas? Okay, I know you've all taken college algebra, so I know you've seen this already. What kind of function have we got? Nobody? Well, let me ask you, does it look like an exponential function? Does it look like a polynomial function? What do you think? Anybody, any ideas as to what we're looking at here? No? Okay. Well, typically functions that are smooth functions like this and that have hills and valleys in them are typically polynomials. Okay, so it's a polynomial function. And more importantly, it should remind you of a quadratic. It should look sort of like a parabola, okay? So you know it's also an even degree polynomial function, okay? It's obviously not quadratic because it's got this wrinkle in the bottom that you don't normally see in a parabola, okay? So basically, you have an even degree polynomial. It could be a fourth degree function, okay? So my comments to you here is, what does question 1, what's it asking you for? Okay, what is this first question asking you for? Hey guys,
Is it for the derivative?
well, do you see a prime?
No.
No, okay, that's great. That's a clue, okay? So what does this notation mean without the prime, the little accent mark? Okay, and anybody else can feel free to answer too. By the way, I don't have the video up, so I don't know who's speaking, so don't worry about it. You're anonymous, okay? So essentially, anybody remember what this notation means? I know you've seen it before.
Is it to find the y?
Yeah, basically it's asking you, what is f of x when x equals -1? Okay, that's what it's asking. And again, I'm having trouble with English. Okay, what is f of x when x is equal to 1? It's function notation. It's telling you what to plug in for the input value and find what's the output value. Okay, so now they gave us this dinky little graph. All right, so we have to kind of estimate where -1 would be. Now it looks like here's -2, and it looks like there's 4 boxes. So it looks like -1 is right here. Okay, I'll try to draw it on my tablet. Okay, everybody believe that's sort of where -1 is? Now what they're asking you isn't to find -1 on the coordinate axes. They're asking you, take it down to the graph and figure out what the y value is. Okay, and they're saying estimate it. So if you look at the y values, now you've got to look this way. Okay, I'm seeing the same 4 boxes between 0 and -2. So I'd be willing to say halfway here is -1. Okay, and I'll do the axes in black and the ones on the graph in blue. Okay, so anybody want to estimate what that y value is?
-1/2.
Yeah, does everybody kind of see how she's getting that? Okay, basically it's halfway between -1 and -2, okay? -1.75 might be reasonable, but take a look over here, okay? Maybe the highlighting will help. Here's -1. The yellow square brings you halfway down to -2, and the pink square brings you all the way down to -2. So I would say probably -1.5 is a better estimate. Okay. But you know what? I wouldn't necessarily mark 1.75 wrong, although more may. Okay. So everybody understand how you're estimating and what it is you're estimating? Okay, so we're estimating the y value here. Okay. So here's an example of them giving you x and you finding y. Take a look at question number 2. Okay, how's question 2 different? What's that asking? Okay. All right. So basically, what they're saying here is, okay, right, Mahmoud? They're saying y is 2, and they want to know what is x. So, what is x when y is 2? That's what they're asking. Okay. All values of x, right, Charlie? Okay. So essentially, it's important to understand how to do this. Now, this is, if you've got a Desmos graph, this is super easy. If you've got something on a TI-84, okay, you kind of need to know how to navigate around. I know some of you have a TI-84. So what I'm going to write next to this here is, on a TI-84, you remember there's a calc menu, okay? So if you have X and you want Y, you're going to use calc value. Okay. If you have your Y and you want X, is you have to graph the Y value and then use intersect. Okay. So this is for those of you who have a TI-84 and you have something graphed in Y1. Okay. So that's where you would be looking at this graph. Okay. So again, the TI-84 is a little clunkier because the technology is kind of old. All right, so if you're doing it on a TI, it's more than one step. Okay, let me clear this. Let's see if I can use a different color. All right, so here's where y is 2 up here. All right, and all they want to know is what are the x values, or estimate these x values. Now notice they're not exactly sitting on an X line, so you might need to do something like this. Okay. So anybody want to try to estimate those X values? Estimate them, okay? So Cecilia is saying -2.25 and +2.25. Good for you, okay? 2 yens is 2.2, -2.2, absolutely. What they're both noticing is this graph is symmetric about the y-axis. You see how this fold happens right here, okay? Right there in the middle, okay? So basically, if you've got one arm of it 2.5 to the right, well, the other arm's probably going to be 2.5 to the left, okay? Or 2.2 or 2.25, okay? So again, I understand that estimating isn't the best on a graph like this, okay? Because it's kind of difficult to see exactly where you are. I would say 2.2, 2.3, or anything in that neighborhood would be good. 2.5, I think, is a little too far over. I think 2.5 might be this line right here, okay? But hey, you know, again, it's an estimate, right? I'm more concerned that you're actually able to understand what the question's asking you, okay? So this was part of the review of functions, okay? The very first unit that we did, okay? Good. Let's look at question 3. Before we actually answer the question, can somebody tell me in English what's domain of a function. What's domain of a function? What does that mean? Okay, feel free to unmute yourself and answer, type in. Okay, Jasmine's saying X values. Okay, can you put a little finer point on it than just X values? What kind of X values? All X values, so all real numbers, is that always the domain? Be a little bit more precise, folks. Okay, what X values in particular, what has to be true about them? Okay, so in other words, I'm asking you, is the domain of every function all real numbers? You know that's not true. So what in particular about the X values allows them to be in the domain? Come on, folks, you can do this. Think of a function that doesn't have all real numbers in its domain. How about a rational function or a square root function? Think of rational functions, okay? There are values, X values, that are not in the domain of that function. What's particular about them? Oops, hold on, I lost my screen mirroring stopped for some odd reason, so give me a minute, I'll get back. Okay, so hopefully you can see that, okay? Anybody remember? Okay, they're the X values for which a function is defined, the function output, okay, y is defined. Okay, everybody remember this definition? They're the X values that give you defined outputs. Okay, if the Y value is undefined for a given X, then that X isn't in the domain. Okay, you might remember for things like rational functions, you would have to throw out the X's that gave you vertical asymptotes, right? Where the function shoots off to infinity, or wholes, because there's no Y value. Okay, with a vertical asymptote, you get closer and closer and closer to that X, but the Y's shoot off forever. You never, have a defined Y value. And a whole, well, there's no point there. There's no Y. It's like a tear in the fabric of the function. Okay. Everybody all right with that? Sometimes this is stated as domain are all the allowed values of X. Allowed is kind of vague. What it means is the ones that give rise to an actual output value. So let's talk about our even degree polynomial. Okay. What is the domain of it? Okay. And again, you want to remember these have arrowheads. What's the domain of this function? Okay. Some more responses, folks. Okay. Yes, I see you're using more notation. Yay. Okay. So I'm getting a bunch of people who say it's negative infinity to positive infinity. Okay. Or all real numbers. Okay. And again, if you look in the chat, the double O thing is the way Moore wants you to type in infinity. Okay. So essentially what you want to remember about functions like this is as these arms go up, they also go out. Okay, so I can go as far to the left as you want as long as I go up far enough. Same thing with this arm. I can go out to the right as far as you want as long as I go up far enough. Okay, And polynomials always have a domain of all real numbers. Okay, so all polynomials have the same domain. All polynomials. So third degrees, fourth degrees, fifth degrees, linear, okay, all have a domain of all real numbers. Okay. As a matter of fact, there are only a few classes of functions that you've learned about that have what are called restricted domains. Okay. Anybody know the families of functions that don't have all real numbers as the domain? Okay, what are the families of functions where you have to worry about excluding values from your domain? I gave you one of them a little while ago when I was describing how to determine domain. Anybody know of any others? Okay, by family of function, I'm thinking polynomial, exponential, logarithmic, that sort of thing. Okay. So polynomials are easy. There's no weirdness in the domain. Rational, absolutely. Jasmine's saying rational, okay? The ones that are fractions with the x in the bottom, okay? Any value of that denominator, any value of that x that makes the denominator 0, whether it's a whole or an asymptote, that's going to be excluded from the domain. So definitely rational. Anything else? Okay. Quadratics are actually polynomials, okay? And quadratics have domains of all real numbers. If you think about it, a quadratic looks very much like this graph, only without the wrinkle, okay? So as I go out to the right, okay, this arm keeps going up and up and up, okay? And I can go out to the right as far as you want without as long as you go up far enough, you can go out to the right. Same thing here. Okay. So again, those are polynomials. Okay. We have another possibility, square roots. Absolutely. Okay. So there are some values. Okay. The values that make it's called a radicand, the thing under the radical sign, negative, are not in the domain. Okay. So let me put that in the chat. The x values that make the radicand negative, okay? So remember, in a square root function, if you try to take the square root of a negative number, you get something with an I in it. You get a not real number, okay? So anything that jumps out of the real number system or has no defined value in the real number system, you're going to exclude those x values, okay? So great, we have rational, we have square root. Okay, how about piecewise? Can a piecewise function have a domain of all real numbers? Okay, think about it for a minute. Okay, the piecewise functions are the functions that have a different rule for a different part of the domain. Okay, right, everybody's saying no, no, they don't. All right, I think it's time to flip over to Desmos. Okay, so let me close this. All right, again, I want to make sure you're not confusing the idea of continuity with domain. Okay, so let's draw piecewise function here. Okay, so y equals x squared And here's the way I do piecewise functions here. I just put the domain in curly braces afterwards. And I'm going to say, as long as x is less than or equal to 1, okay? Here's my first piece, okay? And I'm going to deliberately make this a discontinuous function, okay? And the second piece is y is x plus 2. Okay, let's take a look at this piecewise function. All right. Now, here's my question for you. Okay. Everybody sees the discontinuity in it right here. Okay, so we know it's not continuous. But is the domain of this function all real numbers? Yeah, you're looking at what's in the curly braces, right? As long as x is less than or equal to 1, I'm on the red part of the curve. Okay? When x is 1, I'm right here. So this value, 1, 1, is on the red curve. Okay? Over here, see, it's undefined on the blue curve, which is great, because if it was defined on the blue curve and the red curve, it wouldn't be a function, right? It failed the vertical line test. So all the other values, when x is greater than 1, are on the blue curve. All right, so everybody clear with that? Okay. A lot of times, okay, most times, when you use piecewise functions, the domain is all real numbers. It doesn't have to be, but in most cases it is. Okay. Let's go back to the notes. Okay, and let me ask you another question: is what about exponentials? Okay, is their domain all real numbers? Think about what they look like. Guys, the reason I'm going over this stuff is not just to waste time, okay? If you're going to use functions as models for data, which is most likely what you would do with this stuff in business, okay? If you're going to do calculus on anything, chances are pretty good you built a function model from data, okay? You've got to understand what kind of function models your data, okay? And what are the characteristics of it, okay? Um, and let's take a look. Okay, so basically we're saying negative exponents. Okay, not really sure what you mean. Okay, negative exponents, but maybe we can go back to Desmos and we can play a little bit with it. Okay, I'm going to get rid of these. Okay, so how about an exponential function? Okay, so how about y equals e to the minus x? Okay, would that work as far as a negative exponent? Okay, so here is an exponential that has a negative exponent on it. And I need you to tell me, I'm going to back out of it, zoom out so you can see. What's the domain on this function? What are the allowed x values? Remember, this is going up and it's going left. Okay? Does it matter if it has a positive exponent or a negative exponent? No? Okay. Let's prove that to ourselves. I'm going to backspace over the negative sign. What changed about it? Okay, I changed it from a decay to a growth function, right? It still has a domain of negative infinity to positive infinity. Okay. While we're here, let me ask you about log functions. Okay. Anybody remember anything about them? You might remember this about them. Okay, so let me put my exponential back here. There's my exponential. Okay, and if I want to, okay, I'll put a log function down here. Let me see if I have an ln on my keypad. I'm just going to try typing it. Okay, so why? Okay, take a look. I'll try to close this so it's out of the way. Everybody see that these two functions are symmetric across the line y equals x? They're like reflections of each other. If I draw this line in the middle, okay, the purple line and the black line, okay, are reflected across that red line, okay? That's because they're inverses. But then that changes things, okay? If you look at the log function, which is this black function, okay, is the domain all real numbers? Is the domain of the black function okay, remember, domain are allowed x values. Okay, it's obvious this graph's going all the way out to the right, but what about the left? Maybe if I zoom in a little, it'll be a little clearer. Okay, take a look. Look at what's happening to your x value. Okay. As I travel down the curve, okay, these x values are approaching 0. Do you see the first coordinate getting smaller? Okay. So the x values never reach 0. Okay. You might remember this from a computation restriction, and you can test this on your calculator. If you try to plug a 0 into a log function, it tells you error, domain error. Okay. So basically, you can see this black line can't ever get to the left of the y-axis. So the domain for this log function is 0, positive infinity. Let's see if I can. Okay, so that's the domain. Okay, notice the curved bracket on the 0. You don't ever get to 0, much less anything negative. Okay. Anybody questions? Okay, I want to make sure you have a broad view of this. I realize you're all thinking, why doesn't she just, do the practice thing for the test? Because the test may have exponential functions on it, or it may have log functions on it. I mean, the example is a polynomial, but you need to understand how all of these functions behave if you're going to use them for anything. Okay. So again, the functions that you have to be careful about domain-wise, I'm trying to make a list here: rational, square root, or any even root, okay, and logs, okay. These are the ones where you have to be careful. Rational, square root, and log, okay, tend to have domains that are not all real numbers, okay. Alrighty, everybody good with that? Anybody have questions on it? Yes, no, maybe? All right. I know it's a sticky point because, every time I teach calculus, I know students get stuck here. So that's part of why I'm reviewing it. Okay, let's take a look back where we were. Okay, at the chat. So we found that the domain of this function is all real numbers. What about range? Okay, so what's range? Okay, in this particular example, yes, I'm getting the answer. It's from -2 to infinity, but what does it mean? Here, let me clear my graph. Okay, range has to do with the y values that you get when you plug in the domain to your function rule. Okay, so you take all the values of x that give you an output and you plug them in. What comes out is the range. So one way to do range is to take a ride on the function, okay, and see what you can see on the y-axis. You'll notice this function does not go below this line where y equals -2. You will notice it touches that line. Okay, those 2 points are actually on the line y equals -2. All right, and then you can see from the arrowheads, the function has no limit. It keeps going up forever. Okay, so I would say that a range for this function would be -2 with a square bracket and then infinity. Again, it gets a square bracket because the low spots on the function actually have a y value of -2. Okay, so it touches those. Okay, anybody questions about domain and range? Good. Okay, how about the next question? Okay, what do you want to do when you're talking about whether a function is increasing? Okay, you want to ask. Here's what you're asking: as x increases, y also increases. Okay, so don't let the arrowheads get in the way. I'll get rid of them for now because I find that does get in the way. You're going to move from left to right on your x-axis. Okay, notice as you do that, the y values are coming down here, right? You would have a negative slope there. What about over here? What happens as you go from this point on up? Okay, does everybody see as you go from this point on up, okay, which looks to me like it's -1.5 up to 0, okay, that graph is then going up. The y values are increasing. Okay, so I'd say one interval would be -1.5 to 0. Again, I'm not including -1.5 because right at that low spot, the graph isn't increasing or decreasing. Okay. Then you can see over here from 0 down to what looks like +1.5. Okay, the graph's going down again. Okay, and then from +1.5 on out, the graph is increasing. So the other interval would be +1.5 out to infinity. Okay, now lots of times when you've got two separate intervals like this, you could separate them with a comma, you could separate them with a union symbol. This means or. Okay, does everybody understand the increasing? Okay, everyone understand the increasing question? Okay, right. All right. So that's finding domain and range and guesstimating values from a graph. Okay, it's a lot more accurate to do this algebraically. Okay, so the next section is algebraic. Okay, so Somebody want to tell me, look at question 6. Don't give me the answer. Tell me, how should I do question 6? They're asking me for domain. How would you find the domain? Okay, here's the first step. Look at it and decide what kind of a function it is. What kind of function is it, folks? It's a rational function, absolutely. How do you find the domain of a rational function? What do you do? How do you find a domain of a rational function? Well, it's a fraction with x's in the bottom. Can anything bad happen if you plug in the wrong x value? Remember, we said rationals were one of the ones where we have to worry about domain, in the sense there might be some x's that give us undefined. How do we find those x values? Okay, so let me ask again, how do you find the x values that make f(x)? Guys, if it's too tedious to type in the chat, just unmute yourself for a minute and explain. Okay, so okay, we have one possibility, all right, which is set your denominator to 0. Okay, and again, because this is a fraction, right? That's what a rational function is. What you're looking for is you're looking for values of x that are going to make you divide by 0. Remember, dividing by 0 gives you an undefined answer. Okay, so you're going to set your denominator equal to 0, and then you're going to solve for x. Okay, so I'm going to add 1 to both sides. Okay, and then I'm going to divide by 3. Okay, so basically I have all real numbers except for 1/3. If I plug in 1/3 to my denominator, I'm going to get 3 times 1/3 is 1. 1 minus 1 is 0. Uh-oh. Okay, I'm dividing by 0. So this will give me an undefined output. So I can write my domain in 2 different ways. I can use what's called set builder notation. It's all values of x, as long as x is not equal 1/3. That's one way. And then you can use interval notation, which seems to be what Moore prefers. Okay, so this domain statement is telling you what to throw away. Okay, when you use interval notation, you're giving a list of all the values that are included. Okay, so here's the same domain with interval notation. I'm going to go from negative infinity up to, but not including 1/3. So there's the curve bracket. And then the other half of the domain goes from 1/3, not including it, all the way up to positive infinity with a union in between. Okay, and again, this is most likely to be what Moore will expect you to type in. Okay, everybody all right with that? Okay, everybody okay with finding domain of rational? Okay, so with a rational function, set the denominator to 0. It will tell you what to throw away. All right, not every algebraic calculation is like that. Okay, for example, let's take a look at how do we know it's infinity? Okay, so okay, I think this is the question. The question is, how do I know the endpoints of the domain are infinity? Take a look at this one, this domain statement. This says X can be any number except 1/3. Well, so what are the other numbers? I don't know, anything else, all the way out, okay? So the way you say all real numbers except in interval notation is you start on the left with negative infinity, you go up to the number you want to leave out, and you put a curved bracket around it, and then you start on the other side of that number, so you have another curved bracket, and you go all the way out to positive infinity, okay? So it's kind of like saying it's the whole number line except for these particular pieces, which is where I'm going to have a vertical asymptote in this case, or I'm going to have a hole in some other cases. Okay? Everybody all right with this? Anybody other questions about the notation? Okay, now's the time to ask. Okay, so let's take a look at number 7. Okay, what kind of function is number 7? Yep, everybody's kind of seeing the square root. And it definitely is kind of a weird looking function. I mean, it's got a bunch of things going on there. So I would say the thing you have to worry about domain wise is the square root, right? Because the quadratic part, that's not going to give you any trouble, right? So the square root part is the part you need to worry about. So how do I find, don't give me an answer, like I don't want numbers, I want a process. How do I find the domain of a square root? Anybody want to think about that and give me an idea, a shout out? Square the root first. Okay. Now, you're thinking of solving a square root equation. Okay. And that would be fine if I had like a left-hand side, like a value there. Okay. Like maybe a 0 or a number. I'm not trying to solve it. I'm trying to determine the domain. Think about square roots. Remember we were talking before and we said you can't take the square root of a negative number. Okay, so you want to find out what values of x make the radicand, the thing under the root sign, negative. Can you think of a way to do that? Okay, all right, so we're getting some ideas. Okay, so that's good. Okay, so you could say, I want to know where is the allowed values of x. Okay, so let's do it this way. 7x minus 4. That's called the radicand, all right? And it's the thing under the radical sign. Okay, I said it has to be a positive number. In other words, it can't be negative, all right? So basically positive or 0. So this has to be greater than or equal to 0, all right? If it's negative, I'm going to wind up with i's, okay? I'm going to wind up with imaginary numbers. So these are going to give me not the things to throw away, but the allowed values of x. Okay, does everybody understand that? The thing under the radical sign has to be 0 or greater. All right, then I'm just going to solve the inequality. I'll add 4 to both sides. And then I'll divide by 7. Okay, and if you want to do this in set builder notation, you'd say the domain is all x such that x is greater than or equal to 4/7. Okay, and if you wanted to do this in interval notation, you would say, well, I want the part of the number line that starts at 4/7 and includes it, and then goes all the way out to positive infinity, okay? Because that's what greater than means. So here's the interval notation, 4/7 with a square bracket out to positive infinity. Okay, everybody okay with this? Okay, all right with that? All right. What kind of function is number 8? Okay, look at 8. Okay, usually logarithmic functions have the word log or ln in them. Okay, how can you tell what type of function it is? Okay, look at where x is. Okay, x is up in the exponent. Okay, so when your independent variable, your input variable's up in the exponent, you have an exponential function. All right, so what's the domain of all exponential functions? At least the ones you're looking at. Yeah, okay. I didn't even have to think about this one, okay? Remember, part of the reason I went through the what types of functions do you have to worry about domain was now you know. If it's a polynomial, if it's exponential, I don't even have to think about this, okay? It's all real numbers. And again, if you're not comfortable with it, just graph it and you'll see that it's all real numbers. It turns out this one has some transformations applied to it, but the domain is not going to change. Okay? At most, it moves it from side to side. All right, and now we have our friend the log function. Okay, and that was one of the ones we had to worry about the domain. Okay, what can't be input into a log function? Okay, remember what we said the domains of logs were? They're translated. This one has a translation in it. But what can't you feed log? Anybody remember that? Yes, definitely 0. Something else? Yeah, absolutely. So I can't feed log. See this word here, log base 3? The thing in parentheses is called the argument to log. Okay. When all is said and done, this argument, the quantity in parentheses, must be greater than 0. Okay, so that's how I would do that, right? Okay, so if I want to find out what are the allowed values of x, take the argument to log, the thing in parentheses after the word log, and set it to be greater than 0. Okay, that's what you're allowed to feed it. Okay, then it's easy to just solve. All right, so my domain here is the set of all x such that x is greater than -2. And in interval notation, I'm going to, the lowest value that I can have is almost as far down as -2, but it can't touch it. So curved bracket -2, all the way out to infinity. Okay? Everybody all right with 8 and 9? Okay with 8 and 9? Please ask, okay? Particularly if it's been a while since you took college algebra. Okay? The reason why we go over this stuff at the beginning of a calc class is because you need to be comfortable with it. to use these things as models. Okay. All right, we are at the 1 hour mark. So let me ask you a question. I can stop here and we can do the rest of it on Wednesday, and I can maybe take questions from you guys if you have them, or I can keep going. Okay, so stop here or keep going. Okay, I'm not going to do the whole thing today, but at least I might get through the limit stuff. So vote in the chat. Stop here or keep going. So you just put stop or go. Okay. I'm going to wait for you guys. Okay. Come on, everybody vote. There's like 19 of you on. Okay. All righty. Let's see how we're doing. Okay, has everybody gotten their vote in? Well, the goes win by 3 votes. I'm really sorry, all you stop people. Again, I am recording this. So again, try to hang with us briefly, okay? I tell you what I'll do. There are 28 review questions. Rather than powering through all the limit stuff, I'll stop at number 14. Okay, that's the halfway mark. Okay, so let's just look at these. Okay. So the first, number 10, is asking you about transformations. Okay, so number 10 is asking you about transformations, which essentially means take the graph you've got and transform it. Okay, so they're showing you over here what you've got. Okay, they're saying the graph of f of x is given, and they want you to draw this graph. Okay, so again, that's kind of a dark highlight. Let's try a brighter highlight. Okay, so here they're showing you 2 translations. Okay, does anybody remember anything about transformations that you can tell me what +3 on the end means? What does +3 do to the graph? What does +3 do? Is +3 outside the function? Okay, outside of where f is. I mean x is. This is f of x minus 2 plus 3. What is that telling you? Okay, it's a y-intercept. Okay, remember it's a shift. So how does it shift the graph? Shifts the graph. Okay, remember if it's outside where your x is, it's going to shift up. Okay, so it's going to shift up 3. Okay, the reason for that is anything outside of where your x thing is. Okay, and again, we don't have a rule that drew this graph, but that's what this means. Okay, so for example, if you had f of x being x squared, then x squared plus 3 would take your parabola and shift it up 3 units on the y-axis because it's outside of the function itself. Anything outside affects y, anything inside affects x. All right, how about the -2? What does that do? Okay, remember the X stuff is backwards from what you think. Shifts to the right 2 units, yes. Okay, so here's what we've got. Okay, we have some translations. This is up 2, up 3 rather, and this is right 2. Okay. Can anybody tell me how, if you didn't remember that, okay, because the graph didn't give you a functional rule, you can't just graph it, okay? But if you had a function rule, you could apply the transformations one at a time in a graphing app, okay, and see what they do to the graph, okay? So here's what I'm going to do, okay? I'm going to draw this twice, okay? So the first one, I'm going to do the right 2, okay? So I'm going to look at some critical points here. This looks like it crosses at -7. So if it moves right 2, then that means that's going to have to be at -5. Okay. This point down here looks like it's at -1, -2, -3. That's going to have to move over, okay, and be at -1. Okay, does everybody see how I'm shifting it to the right 2 units? Okay, and then the last critical point is this thing right at the origin, and if that moves over to the right 2, that'll be here. Okay, so I'm going to graph the critical points, and I moved each one of them to the right 2 units. Okay, so my graph should look something like this. Okay, and that's just with the first, the right 2 transformation applied. Okay, now I'm going to do the final graph, and I'm going to take this graph and shift it up 3 units. So that's easy. I'm just going to count 1, 2, 3. That point moves up here. This point's going to move 1, 2, 3 here. And this point's going to move 1, 2, 3. Okay, so my final graph would look like this. Okay, so the red graph is the final graph. Okay, anybody questions on the transformations? Questions on transformations? Okay, transformations again are important in model building, especially the up-down transformations that determine your vertical intercept. They're your starting value in your model. Okay, so you kind of need to know where those are. All righty. Okay, we've got at most a few more to do, folks, so hang in there. Okay, I'm going to stop right here today. So let's talk about this. We may not get this far depending on how many questions there are. As a matter of fact, I noticed from looking at homework, a lot of you kind of struggled with the idea of a limit, especially that one homework problem where you had to draw a graph that corresponded to the limit statements, and then I went in and I looked at them. Okay, please do look at my comments, okay, on your homework, or when you do a grade check, look at my comments, obviously, because that's how I keep up a dialogue with you. Okay, again, given the fact we're not meeting in person, we kind of have to use the communication tools we have. Right? So let's take a look at this first one, number 11. This is asking you, what is the limit as x approaches -2 from the left? Okay, limit as x approaches -2 from the left. Okay, so I just want to point this out. Okay, this -2 is the x value you're getting close to. All right, and this negative sign means you're approaching it from the negative part of the x-axis. That means you're coming at it this way. Right? So I'm getting close to -2. What is the y value that I'm approaching? Is there a y value I'm approaching? What's 11? What's the answer to 11? Okay, the limit as I'm approaching -2 from the left. What value am I getting close to? Right, everybody sees 2, right? I'm getting close to the value right here. Okay. This next question is asking you for the limit as x approaches -2 from the right. Again, if you take a look at the notation, the -2 is your x value, and the fact that you've got a plus sign here now says you're approaching it from the other side. Let me switch colors. Okay, so we don't get confused. There's my -2, and then I'm coming at it from the right. Okay, so as far as that's concerned, we've got this. Okay, and you can see I'm approaching 0. Okay, all right. Okay, everybody comfortable with that? Again, don't let the arrowheads at the bottom of the graph confuse you. Okay, it's what direction you're approaching the x value from, left or right. Now here's the $64,000 question is, so what about the limit as x approaches -2? Notice there's no from the right or from the left here. So this is asking you limit as x approaches 2. Okay. Notice what happened in 11 and 12. We got 2 different answers. So can we come up with an answer for 13? Yeah, exactly. Very good. Does not exist. Okay, and the reason for that is you got 2 different answers. Okay, you got 2 different answers. So in order for a limit to exist at a particular x value, the value as you approach it from the left and you approach it from the right needs to be the same. Okay. Okay. This is a good space to stop. Okay, so I'm going to stop here. All right, and we'll continue with this next time. Okay, because again, the other limit questions are about this point up here. So this is a good place to stop. I'm going to stop sharing my screen for a minute. Okay, and come back to the meeting. And again, before we end for today, let me ask, does anybody have a type of a problem that you want to share? Okay, some sort of a problem that you particularly had trouble with. Okay. Okay, nobody has anything to share? Okay. Have any questions on anything in the practice so far? Okay. Again, if you're not comfortable sharing here, please feel free to email me and I'd be happy to work with you separately. But what we'll do on Wednesday is we'll finish the rest of this review. So from question 14 on until the end. And again, I strongly urge you folks, if you have questions that you think would be interesting and to go over, bring them. Okay, it'd be great if you can share them in advance. That way I can queue them up so everybody can see them. Okay, but just bring them. All right. Otherwise, that's all I have for today. I'm going to stop my recorder.